Welcome to the deep dive.
Huh.
Sometimes you read a study and it says no significant difference found. Ever wonder, does that really mean nothing's going on?
Or, yeah, was a study maybe just not sensitive enough to pick it up?
Exactly. And that right there is where this idea of the power of a statistical test comes in.
Mm-hmm.
So today we're diving into statistical power, what it is, why it matters for anyone looking at data, really.
Right. Think of it like this. Power is the probability that your study will actually detect a real effect, assuming one, actually exists.
Okay, so it's about avoiding that mistake of concluding nothing to see here when there really is something, a false negative.
Precisely. It helps us understand how confident we can be when we don't find a significant result. Low power means, well, maybe we just missed it.
All right, so how does this power thing work? Is there a way to calculate it? I
Yeah.
feel like I learned this once.
Oh, yeah. Well, fundamentally, it's a probability, and it's influenced by a few key factors. First, there's a significance level you set, your alpha. That's your risk of a false positive.
Okay, alpha. Got it.
Then there's the actual size of the effect you're hoping to find in the real world. Bigger effects are easier to spot.
Makes sense.
And finally, how much variability or noise there is in your data. Less noise makes the signal clearer.
So alpha, effect size, variability, they all play together.
They do. There are formulas, of course, but the core idea is that interplay. You juggle those things to influence your test's power.
So thinking practically, if I'm designing a study and I want more power, a better chance of finding a real effect, what levers can I pull?
Good question. Well, you could increase your alpha, accept a higher risk of a false positive, but that's often not desirable.
Right, usually you want to keep alpha low, like 0.05.
Exactly. A bigger factor is often the effect size. Now, you can't change the real effect size.
But maybe you can study effects that are likely to be larger, or design the intervention to be stronger.
Sort of, yes. Or focus on outcomes where you expect a bigger impact. Also, crucially, you can try to reduce that variability maybe through more precise measurements or a more homogeneous sample.
Less random noise in the data.
Yep. And sometimes using a statistical test that's more tailored to your specific hypothesis can be more powerful.
You mentioned effect size being easier to spot if it's bigger. That seems intuitive.
Totally. It's like trying to spot an elephant in a room versus trying to spot a mouse.
Haha, okay, yeah. The elephant's hard to miss. Much higher power for detecting elephants.
You got it. Larger effects naturally give your study more power.
What about sample size? The number of participants or data points? That feels huge.
Oh, it's absolutely critical. Probably the most common way to increase power.
More data, more information.
Exactly. More data helps you separate the real signal from the random noise. Think of it as getting a clearer, higher resolution picture. Larger samples almost always mean higher power.
Which is why those big clinical trials need thousands of people sometimes.
Precisely. Especially if they're looking for a small but important difference between treatments. They need that power.
Now, I keep hearing this number of 0.8 or 80% power. Why that specific target? Seems kind of arbitrary.
It is a bit of a convention, honestly. It emerged as a common standard, sort of a balance.
A balance between what?
Between the risk of a false negative missing a real effect, which you want to minimize, and the practical constraints of research, like time and money. 80% power means you have an 80% chance of detecting the effect if it exists at the magnitude you expect. It's generally seen as a reasonable goal. Not perfect, but reasonable.
Okay, so if we're aiming for that 80%, how do we know how big our sample needs to be before we start?
That's where power analysis comes in before you collect data. It's a planning tool.
So you work backwards.
Kind of.
Yeah.
You decide on your desired power, like 0.8. You specify your alpha, usually 0.05. And you have to estimate the effect size you're trying to detect, maybe based on prior research or what you'd consider practically meaningful.
Right. The smallest effect you care about finding.
Exactly. Plug those into a power calculation, and it tells you the minimum sample size you'll likely need.
That seems incredibly useful for planning.
Mm.
Avoids wasting resources on underpowered studies.
It really is essential for designing efficient and ethical research.
Do you need to be a stats whiz to do this? Are there tools?
Thankfully, no. There's lots of statistical software now, R, SPSS, dedicated programs, and even online calculators that can run these power analyses for common tests. Makes it much more accessible.
Good to know. Okay, one more thing. One-tailed versus two-tailed tests. Does that affect power?
It can. If you have a very strong reason to believe an effect can only go in one direction, A one-tailed test focuses all your statistical attention there.
So for the same sample size, it could have more power.
Yes, if the effect is genuinely in that direction, but the big risk is if the effect happens to be in the opposite direction, even a large one, a one-tailed test will completely miss it.
Ah, so you need to be really sure about the direction beforehand.
Absolutely. Two-tailed tests are generally the default because they cover both possibilities.
Lastly, what about calculating power after a study is done? Post-hoc power. I've heard that's controversial.
Yeah, it's generally frowned upon by statisticians. The problem is that observed power, calculated after the fact using the results you got, is directly tied to your p-value.
So if you got a non-significant p-value, your observed power will just be low.
Pretty much. It doesn't really add new information beyond what the p-value and confidence interval already tell you about the uncertainty. It doesn't tell you about the power the study would have had for a different, perhaps plausible, effect size.
So planning power beforehand is key, but calculating it afterwards isn't that helpful.
That's the consensus, yeah. Focus on a priori power analysis for design.
Okay, so wrapping this up, understanding power is crucial because it tells us how likely a study actually was to find something if it was there. It stops us from just assuming no effect when maybe the study just couldn't see it.
Exactly. It adds a critical layer to interpreting results, especially those non-significant ones. Makes you think about the study design, the sample size.
So the next time you encounter research findings, especially if they report no significant difference, maybe pause and think. Was the study powered adequately? Could it realistically have detected the kind of effect it was looking for? Something to chew on.
Definitely a good question to ask.
Thanks for breaking that down. That was really insightful. And thanks to you for joining us on the deep dive.